All right, let's take a look at the lab It's Hot in Here. So pre-lab, there's a couple of terms, correlation and causation. A correlation is when there's a mutual relationship or connection between two or more things, and a causation is the act of causing or producing. So the first question that it wants you to answer, do you think the relationship between increasing levels of carbon dioxide and increasing average temperatures on Earth is a correlation or a causation? Why? And so go ahead and pause the video and write something down for that. The second question here is, how can you investigate whether two variables are simply correlated or if one variable is actually causing an effect on the other? So if possible, you want to isolate the variable you are studying, which is exactly what we're going to do today in this lab. We are going to isolate carbon dioxide, manipulating that to see if it causes a change in the rate of temperature change. Lab time. So here's the scenario. Long before social distancing began, your friend Snapchatted you this picture from the concert that she was at. Bonus points if you can name this artist. It is Lauv. She complained about how hot it was in the crowd. You know that the human body just radiates thermal energy, but you also wonder if all the carbon dioxide exhaled by people in the arena and the fact that there's so many bright lights shining down from the stage could also have an effect on the temperature as well. So you ask another friend, and this friend says, no, carbon dioxide actually would have a cooling effect because fire extinguishers contain pressurized CO2. So that carbon dioxide would cause the concert venue to actually cool down if it were the only factor. So she proposes that it's only getting hotter because human bodies radiating energy overwhelm this cooling effect of the carbon dioxide. So you write a hypothesis. What is the effect of carbon dioxide on the temperature in a system with light energy? So if CO2 levels go up, the temperature inside the closed system with light energy added will do what? Because why? So pause this video and give yourself a chance to write down a hypothesis here. Okay, and then let's investigate. It says you will measure change in air temperature over time when a light bulb shines on a controlled system, the air inside a 2-liter bottle. And part one, you're going to do it with a, quote, empty concert venue, and there's no people exhaling, so the level of carbon dioxide is just what it is outside in the atmosphere. And part two is you're going to simulate a lot of people breathing, exhaling carbon dioxide. So you're going to add carbon dioxide to the bottle and see if that changes how fast the temperature goes up. Okay, so what will your manipulated variable be? The amount of CO2. Your responding variable will be the rate of temperature increase. So how fast is the temperature increasing? What variables should be controlled for? Well, it kind of helps to watch this lab video first so that you can actually see, how this is working. But you definitely want to keep the distance from the heat lamp to the bottle constant. You also want to preheat the heat lamp. So it gives off consistent heat. Like you wouldn't want to start it where it's just turned on, because then it's kind of starting to warm up. And so it might give off less thermal energy at the start. So those are the kind of things we want to control for to make sure we get accurate results. Okay, so materials, we're going to use this program called Logger Pro, temperature probe, the plastic 2-liter bottles with the tops cut off, a heat lamp, a cup to act as a lid for putting the temperature probe through. So if you haven't already, please pause this video and watch the YouTube of the actual lab so that you can see these procedures carried out. Okay, because I'm going to kind of skip over that and assume that you've watched that. Okay, then we're going to look at our data here. So our data is time versus lower CO2 and higher CO2. So you definitely want to add this row if you haven't, and you can do that by right-clicking and going to Insert, and it'll just insert one for you. So I'm going to delete that. Okay, so, and then if you wanted to make something bigger, you can just go right in between, click, hold, drag to make it a little bit bigger. Okay, so we've got time versus lower CO2 and what happened as the light was shining on the bottle over 50 seconds, and then higher CO2. So I'm going to select all my data to make this graph, and I'm going to go to Insert, and I want this scatter plot right here, top left one. Okay, then I'm also going to want to add an axis, the primary horizontal, and I want to add primary vertical. And I'm going to label these. Going across the bottom is time in seconds. And the x-axis, I can get it, is temperature in degrees Celsius. And our title might be something like the effect of added CO2 on the rate of temperature increase in a closed system with constant thermal energy. Wow, this is not my most concise title, but it's definitely explaining what's going on. Now, we'll give ourselves a little more room. This graph is not very spread out. So if I right click and go to Format Axis, I can actually have my minimum be, let's see, what was the minimum? 24. So maybe let me do 23. And my maximum, yeah, be 33. Then see my lines are a little bit spread out. And then if I go to the lower CO2 and add a trend line, I can scroll down off to the right here, display equation on the chart. So you can see my slope is 0.1234. That's kind of cool. And then if I right click on the orange line, add trend line, go to display equation on chart, I can see this one has a slope of 0.1546. So when there was more CO2 in the bottle, the temperature did go up faster. Okay, so I think we want to paste our graph in there then. So let me go ahead and copy this into my OneNote. There we go. Okay. Which line, the one from the empty concert venue with low CO2 or the one from the packed concert venue with higher CO2 has the steeper slope? This one, the packed concert venue. What conclusion can you draw from your results about the effect of increased CO2 on the rate of temperature increase? Increased CO2 causes an increase in the rate of temperature increase. So notice I used the word cause there. Okay, it says consider your results and make a claim about the relationship between carbon dioxide and air temperature when light energy is added to a system. As the amount of carbon dioxide in a closed system increases when light energy is added to a system, the temperature increases at a faster rate, resulting in a steeper slope. Think back to your two friends. One at the Key Arena concert with a building amount of carbon dioxide under all the lights from everyone breathing. Another who predicted the presence of CO2 would not be a contributing factor. What evidence could you give to your friends to support your claim? When the CO2 was lower, a rise in temperature was slower, and the slope was only 0.1234. When the CO2 was higher, the rise in temperature was more dramatic, and the slope was 0.1546. We can't really write a reasoning section yet because we need to learn more about why a higher amount of CO2 results in a more dramatic temperature change. So let's do a simulation. The phenomenon that we just experienced has a name. It's called the greenhouse effect. And in case you're not familiar with the greenhouse, it's a building made of glass. It allows sun to get in, but then it traps the heat inside. So the building stays warm even when it's cold outside, so even in the winter. That's why it's great for growing plants, and they call it a greenhouse because lots of green things are growing in there. Because gases in the Earth's atmosphere also let in light but trap heat, many people call this phenomenon the greenhouse effect. The greenhouse effect works somewhat differently from an actual greenhouse, but the name stuck. So that's how we refer to it today. So in this next activity, we're going to use PhET, the simulation right here, to explore which gases fall into the category of greenhouse gases and learn how visible light from the sun is transformed into thermal energy and where it goes. Okay, so click on this link, and it says just start by playing around with each of the tabs. So when you open it, you're going to see the greenhouse effect, glass layers, and then photon absorption. So pause this video and just take a minute and play around with each of these. Okay? And it says in the photon absorption lab, circle which gases are able to absorb infrared photons, aka thermal energy. So infrared photons, and you had to, I think, kind of add this. Let's click on CH4 first. CH4 wiggles, so that means that it can absorb. Let's check CO2. Yep, that absorbs. Let's check H2O. Yep, that can absorb. Let's check N2. No. Let's check O2. No. Okay. So we want to circle CH4, CO2, and H2O. Now let's think back to our lab and complete the reasoning for your claim. Record your answers here. So it makes sense that a higher amount of CO2 results in a greater temperature change in the same amount of time Because CO2 molecules are able to absorb thermal energy, or you could say infrared photons. Notice that in addition to an infrared photon being released, the CO2 molecules wiggle or vibrate. Consequently, some of the absorbed photon energy is transformed into blank energy, which leads to the increase in temperature. Kinetic energy, the energy of movement. Now let's talk about what it was asking in letter B. After a gas molecule absorbs an infrared photon, you may notice that it's re-emitted, it's released. What time does it move toward the top of the screen, and what time does it move toward the bottom of the screen? Hint, it should be around 50-50. So let's watch it together. Let's do a CO2. It's wiggling, it's re-emitting down. It's wiggling, it's re-emitting down. 3 down in a row. Come on, we need an up. That one was sort of neutral. Okay, 2 went up, another one went down, another one went up, another one went down, another one went up, another one went down, another one went up, another one went up, another one went down, another one went down. Seems like more are going down than up, but it should be about 50-50. Okay, so you get the point. So what does that mean? Well, 50% of the time, when you have the CO2 molecule, the infrared photon, the thermal energy, is re-emitted back to space, back up towards space. And another 50% of the time, the thermal energy goes down to Earth. Okay, and this contributes to the bouncing around effect that you'll often see in pictures of greenhouse gas effects. They'll show the Earth, and they'll show the atmosphere, and they'll show, okay, carbon dioxide molecules, which are like this, and then thermal energy is just kind of like bouncing around before it eventually radiates out into space. But it gets trapped here because of this, all these carbon dioxide molecules that it gets absorbed by. And we're going to see that coming up. Visible photons, light, are never absorbed by gas molecules, but they can be absorbed by other things like a sandy beach and transformed into thermal energy. What do you think happens when a visible photon hits a puffy white cloud? Well, if we go to visible photon, we'll see just what they're talking about, that none of these are able to absorb. I wish we could do something where we build a cloud. I think, is there a way we can add a cloud on this one? Number of clouds, here we go. So the visible photons are the yellow ones. Let's see if they have it do anything. Yes, they scatter. So they can definitely scatter around and bounce off of these clouds. So you can see that in this one. Okay, so they scatter. So in the glass layer tab, it says, notice the initial surface temperature of the Earth at a glass pane. Can you imagine how silly it would look if there was a piece of glass hovering over your head at all times, not to mention dangerous? Then it says, why do some of the infrared photons disappear into the glass pane and then come back suddenly, moving either toward the surface of the Earth or into space? So let's go to the glass layers and let's add a glass pane. Okay, so notice that some of these infrared, the red molecules, are getting absorbed, they disappear, and then eventually they're re-emitted. And they come out in different spots. So some are re-emitted back down and some are re-emitted back up. Some seem to stay in there for a while. So the glass absorbs the infrared radiation, aka the thermal energy, and then they come back suddenly, but re-emits it. So this should be familiar. What acts like a glass pane in the atmosphere? Greenhouse gases. That's exactly what they do. They absorb the infrared radiation and then they re-emit it. So they kind of trap it for a while. So let's go back to this just for fun. I want to show what happens if I add a bunch of glass panes. You can see the temperature is going up overall because everything's just getting trapped more. So all these are like representing greenhouse gases. It's just they're getting stuck. They can't leave because there's all this glass trapping them. Okay, so back to the greenhouse. Sometimes you'll see, like if you follow a red molecule, like it's just bouncing around. You see, it looks like a glitch. That's not a glitch. Those molecules are hitting invisible carbon dioxide and other greenhouse gases. So they're being absorbed and then they're being re-emitted. So how can you tell? You can see the infrared photons glitch out. So they stop and change directions. Change the greenhouse gas concentration to be 0 and see what happens. Okay, so greenhouse gas, none. Let's watch the temperature here. So 284, 283, it's going down, it's going down. We get rid of our clouds too. So rather than these little molecules hitting a greenhouse gas, look, they never glitch out. They just radiate back into space. So it is good to have greenhouse gases because otherwise, look at the surface temperature of the Earth. It's already at -3 Fahrenheit. It's going to be cold. And so the Earth would basically be not a fun place to live if there were no greenhouse gases. And it's also not a fun place to live with too much greenhouse gases. So, missing a parenthesis there, too much of a good thing. Without any greenhouse gases, without any greenhouse gases, Earth would be freezing. But with too many, Earth is getting too hot. Hence the name of this lab, Hot in Here. So tying it all back to the lab, the carbon dioxide molecules are sort of like invisible blankets around that temperature probe. And so they're getting trapped around that longer, and that's why the temperature keeps going up. All right, final questions. The concentration of CO2 in the atmosphere today is a little above 400 parts per million. The concentration of CO2 in the atmosphere in the mid-1700s was only 280 parts per million. Based on the lab experiment, Do you think there's a correlation or a causation between the increased CO2 and an increase in Earth's temperature? I hope you can see now that it's a causation. We isolated CO2 and saw that increased CO2 increased the rate of temperature change, increase the rate of temperature increase. And the key is that we were able to isolate it. And then last but not least, what do you think the effect of COVID-19 was on CO2 emissions worldwide? Do some research. So one thing that I've heard, I was reading the Bill Gates climate book, and emissions went down 5% in 2020. It kind of seems like they should have gone down more, was what he was saying too. Like it was really a good thing, and if we could keep that trend going, that would be amazing. But obviously that came with a lot of cost to our economy. And so we've got to figure out how we can decrease the carbon emissions. So go ahead and do your own research on this, do some Googling and figure out the answer to this. Have fun with it. All right, that's it.